Today we're going to further our discussion on centripetal force. You'll remember from last Tuesday that centripetal force was just the force that is causing the object in circular motion to be pulled toward the center. If left to its own, the object would keep flying in a straight direction, so something has to be pulling it in, working against inertia. If you think back to the example of the child who was being swung by his sister, the centripetal force was caused by the tension on the arms as they're holding each other. When you think back to the homework illustration you had with the person swinging the scale, the centripetal force was the tension on the string that was holding the scale and the scale itself. So typically at this point we've talked about centripetal force as originating from tension on a rope or wire or something of that sort, pulling the object back in. Well, today we're going to look at a different cause of centripetal force, and that's going to be gravitational force. Gravitational force is simply the force that causes objects to be accelerated toward the center of a mass. In terms of the statement of it, I'm going to give you the full statement, and I will expect you to learn this. This is actually a fairly significant law, and the law is actually made in the statement, and from the statement you can get the formula, which we'll see in a little bit. The statement is the gravitational force between two objects Okay, I'm already giving up on this one. Sorry. Gravitational between two objects, gravitational force between two objects, the force that pulls an object in towards the center, is directly between two objects. Well, I'm just getting ahead of myself. Is directly proportional, which means that as one increases, the force also increases. As both increase, then the force increases proportional to that. So it's directly proportional to, and I want you to consider what it would be proportional to. What would I need to increase to cause that force to be greater? You think of gravitational forces as existing between an object and a planet, or the object and the moon. So you're thinking of these extremely huge objects. That is true and most obvious there. It is going to be actually existent between any two objects at all. But what would I need to do to those objects in order to increase the gravitational pull between them? Think about it for a moment. Did you come up with the idea of masses? Because that's actually what will increase their gravitational pull. It's directly proportional to the product of their masses. And again, that simply means that as I increase either or both of the masses, I am increasing the gravitational force between them. But I'm actually going to say and. Indirectly proportional. Think in your mind, what does that mean when it's indirectly proportional? I think you have enough math skill to know that indirectly proportional means that as I increase one, I decrease the other. So what would I have to increase in order to decrease the gravitational pull between two objects? Think about that for a moment. How do I experience less pull from the Earth to me? What do I have to do to have less pull? Did you come up with the idea of get farther away? Because that would be true. Indirectly proportional to the square of the distances between them. Of the distance between them. And by the way, this law, this relationship is often true with forces. You're going to find that this statement of this law is almost exactly the same as the statement of Coulomb's law, which we'll be hitting later on in second semester. So the gravitational force between two objects is directly proportional to the product of their masses. As I increase the mass, I increase the gravitational force, and indirectly proportional to the square of the distances between them. As I increase the distance, I decrease the gravitational force. Now, there's mathematical ways of writing these things. I don't think we've talked about this yet this year, but there's a mathematical expression for proportionality, and it looks like this. The force is directly proportional. It's supposed to be an alpha symbol. Directly proportional to the product of the masses. Product means what function is going on? Multiplication. So it's m1 times m2. That's how I would write a proportionality. Force of gravity, and I'm going to make this a little g. The force of gravity is directly proportional to the product of their masses. Any idea how you would write an indirect proportionality? I've had students try to make the fish go the other way for my alpha symbol, make it go down for my alpha symbol. But really the only way you can do an inverse proportionality is to put one of the two things in the denominator. So it's going to look like this. F sub g is inversely proportional. 1 over makes it inversely proportional to the square of the distances between them. And of course, we've been using radius for these distances. And it happens that you can overlap proportionalities and make it into one statement. So I could say F sub g is equal to is proportional to m1, m2 all over r squared. It's proportional to. Here's the problem. If you look on your calculator for a proportionality button for an alpha symbol, not alpha like A-L-P-H-A like the alphabet, I don't mean that. But if you look on your calculator for a proportionality symbol, you won't find it because it's only about relationships. You're not going to get an actual number out of it. If I double the mass, I'm going to double the force of gravity, that kind of thing. I can only tell you what will happen as I change one. I can't give you an actual answer. If I want to get actual numbers to it, I have to turn my proportionality into an equality. And here's the statement that I'm going to use if I have not already. You can convert a proportionality into an equality by doing something to it that you already understand. Let's talk about a circle. The circumference of a circle. Circumference is directly related to the diameter. As I increase the diameter, I increase the circumference. Okay, that makes sense. If I double the diameter, I double the circumference. That is the proportionality. What I do to one will happen to the other. But as we're working with circles, we really want to know, okay, but exactly what circumference will I get if I do this to the diameter? And that should start looking familiar to you. How do I go from diameter to circumference? You're using the formula I'm sorry, somebody is here and I'm going to ignore it. You're using the formula circumference is equal to pi d. How did I get from here to here? I included a constant. I can always go from a proportionality into an equality by the inclusion of a constant. So that's how we're going to finish out our statement. You can convert a proportionality into an equality by the inclusion of a constant. I apologize for that interruption. So now what I need to do is find the constant that relates the force of gravity to the masses and to the distances between them. The formula is going to be F sub g is equal to capital G, and that is my constant, m1, m2 all over r squared. So the only difference to make it into an equality was putting in capital letter G. Capital letter G is called universal. And by universal, it truly is universal. This works everywhere in the universe. Universal gravitational constant. And as a number, G is equal to 6.67 times 10 to the negative 11. Now, what I want my answer to turn into is newtons. So I need to put newtons into my constant, but the constant also needs to have units in it that will take away everything I don't want. So I'm going to start out with newtons. I definitely want newtons so that when I'm all done, newtons stands. Let's see, I have m1 and m2 in the numerator. So I have kilogram times kilogram in the numerator. So that means I'm going to want kilograms squared in the denominator so that it will cancel out with my kilograms squared in the numerator. I'm also going to end up with meters squared in the denominator with my r squared. So for my constant to get rid of that, I'm going to need meters squared in the top. So the constant is 6.67 times 10 to the negative 11 newtons times meters squared all over kilograms squared. Okay, let's go ahead and apply this and see what this looks like in a problem. If the Earth is 1.5 times 10 to the 11th meters from the Sun and has a mass of 5.98 times 10 to the 24th kilograms, what is the mass, m sub s, of the Sun? Now, you don't have a lot of information here. What I would really love you to do, and I'm going to have my face-to-face students do this. I'm going to just set them loose and say, okay, figure it out. What do you know? What do you know about the Sun and the Earth? Think through everything you know about the Sun and the Earth. How is that going to help you to find the mass? If you need to, stop this for a little bit and play with it. See if you can get this. Okay, hopefully you did step back and try this. Here is the key to this whole thing. If you have an orbiting object, so here's the Sun, here's the Earth going around the Sun, it is orbiting, it is accelerating. The only way it can accelerate is if there is a centripetal force acting on it. The only way it can keep from flying off into space is if there is a centripetal force acting on it. Now, in the past, centripetal forces have been some kind of a tension with a connection between the two objects. There's no giant string attached to the Earth keeping it in the orbit. So what is the only thing that is holding the Earth in place in its orbit? That thing is gravitational force. So the centripetal force is the gravitational force. If I know the one, then I can find the information I need from the other. But boy, it feels like we don't have a lot of information here. So let's see what we've got. We know that the mass of the Earth, and I'm just going to put a sub e, is 5.98 times 10 to the 24th kilograms. I know that r is 1.5 times 10 to the 11th meters. So if I try to jump into this equation, I'm not going to be able to do it. I don't have enough information. I don't know what F sub g is, so I can't find the mass of the Sun. So I'm going to have to come at it through the back door. I do know this. I know that my angular velocity is 2 pi all over 365 days, which converts to 2 pi all over 365 days in the year, times 24 hours in the day, times 60 minutes in an hour, times 60 seconds in a minute. And when I do all of that math, I end up with 2 pi over 3153600. 3600 seconds. And that turns out to be 1.99 times 10 to the negative 7. Radians per second. So I have enough information to find F sub c. I have m, and the mass is always the mass of the object doing the orbiting. So in this case, it's going to be the mass of the Earth. It's the mass of the object being accelerated. F equals ma. The force acting on a mass causes it to accelerate. So the mass that's being acted on is the mass of the Earth. So I know that F sub c is equal to, and I'm just going to throw it all into one equation, F sub g, which means that m r omega squared is equal to g, mass of the Earth, mass of the sun times mass of the Earth all over r squared. It's the same r. Here I'm talking about the centripetal acceleration or centripetal force using angular velocity. Here I'm finding the centripetal force as in force of gravity. It's the same object, same distance, same r. But one nice thing that I see in doing this is that my mass of the Earth cancels out. I don't even have to bother putting that into the equation. So what I have then instead is 1.5 times 10 to the 11th, which is the distance from the sun to the Earth, my r, 1.5 times 10 to the 11th, times 1.99 times 10 to the negative 7, and don't forget to square it. Don't forget to square it. Is equal to 6.67 times 10 to the negative 11, that's my capital G, times the mass of the sun, which is what I don't know, so I'm just going to leave it as m sub s, all over 1.5 times 10 to the negative 11 quantity squared. These do not cancel out. I could cancel out the mass of the Earth and the mass of the Earth because they were on opposite sides of the equal sign, but in the same position. They were both in the numerator. So if I multiply both sides by 1 over m sub e, then it cancels out on both sides. I can't do that here. I cannot do that here. So what I have to do is move it over by multiplying both sides by 1.5 times 10 to the negative 11 over 1, quantity squared rather, over 1. And I'm also going to move this at the same time by dividing both sides by that. So I end up with this, 1.5 times 10 to the negative 11, quantity cubed, times 1.9 times 10 to the negative 1.99 times 10 to the negative 7 quantity squared, all over 6.67 times 10 to the negative 11, and that ends up being the mass of the sun. Do the math on that, and you end up with mass of the sun is equal to 2 times 10 to the 30th kilograms. 2 times 10 to the 30th kilograms. All right, so here's a big key that I want you to know. For an orbiting body, this will always be true. For an orbiting body, centripetal force is equal to gravitational force, or gravitational force is the centripetal force. They're the same thing. They mean the same thing. They create the same effect. They are the same thing. All right, next page. One more problem here. Most communication satellites, gotta get here, most communication satellites remain in orbit above the same point in the Earth. That's called geosynchronous. This requires that they circle the Earth once every 24 hours. Their motion is synchronous with the Earth's rotation, also known as geosynchronous rotation. So this is what I mean. So let's say that I have the Earth, I'll move it up here so I have more room. Let's say that I have the Earth right here, and London is right here, and we're looking down from the top. So London is right here, and as it goes around, if there is a satellite above London, then the satellite has to go around and keep pace with the rotation of the Earth. So it stays above London the whole time. It is rotating at the same angular velocity as the Earth is. At what distance from the Earth should a satellite be placed if it remains geosynchronous? All right, let's figure out what we know here. And it doesn't feel like we know very much. What I do know is that what is making it stay above the Earth is the force of gravity. Otherwise, it would fly out into space. So I know that the force of gravity is going to be my centripetal force. Let's write down what I know. I know the mass of the Earth. I was just given the mass of the Earth is equal to 5.98 times 10 to the 24th kilograms. And let's see, what else do I know? Well, if it's geosynchronous, I know that its angular velocity is 2 pi per day, which is the same as 2 pi per 24 hours in a day times 60 minutes in an hour times 60 seconds. You do that, and we've done this before. It's 7.27 times 10 to the negative 5 radians per second. And it really feels like I don't know a whole lot. In fact, that feels very, very sparse. And what I'm looking for is R. R is equal to, I don't know. Boy, let's just set this up and see what we can do with this, because it doesn't feel like we have enough information. But let the magic of math take care of this for us. So I don't know the mass of the satellite, but I do know the R. That's what I'm looking for, is R. But I do know omega, 7.27 times 10 to the negative 5. But don't forget that you need to square it. Is equal to G, 6.67 times 10 to the negative 11, times the mass of the Earth, which is 5.98 times 10 to the 24th, times the mass of the satellite, all over R squared. Well, let's see, that's taken care of. Oh, look, I have only one variable left. All I needed was to find the mass of the Earth and to find the angular velocity. The rest takes care of itself. So I move my R over to that side, and I'm left with R cubed is equal to, but now I'm going to move this over here by putting it into the denominator. So it's going to be 6.67 times 10 to the negative 11 times 9.81. That's just habit, isn't it? Times 5.98 times 10 to the 24th, all over 7.27 times 10 to the negative 5 quantity squared. All right, now this is just calculator stuff. Don't forget, when you're done, you're taking the cube root of it. If you do the math, you're going to find that R cubed is equal to 7.55 times 10 to the 22nd, and R is equal to 4.23 times 10 to the 7th meters. Now, if you don't have a cube root button on your calculator, you do have you probably have a button that is the y to the x power or x to the y power. And what you're going to hit for the y power then would be 1 over or 1/3, 0.33333, and that will get you what you need to be. So for your x to the y power, you're going to make it your y power 0.333, as many threes as you can get in there. I don't know if you have, there is also an x to the 1 over y button on mine. It's a shift function on mine, in which case then I can just raise it to the 1/3 power, because you remember that this is what you're raising it to as an exponent. This is the root you're taking in the denominator. So if I raise it to the 1/3 power, then I'm going to actually get the cube root out of my calculator. All right, and what speed should the satellite be? Let's see, I know my radius, I know my angular velocity, and I'm looking for tangential speed. I think that's a v is equal to r omega equation. And it's going to end up being v is equal to my radius, which I just found, 4.23, times 10 to the 7th, times omega. This time it's not squared, so it's going to be 7.27 times 10 to the negative 5. And my answer ends up being 3,080 meters per second. That's going pretty fast. All right, now it is also possible to associate weight with your gravitational pull, because your weight is the force of gravity on you. So if you have a problem in the homework that says, what would your weight be on Jupiter? Weight is equal to force of gravity. Remember we said that the definition of weight is the expression of gravity as a force, the force of gravity, the expression of gravity on your mass. So it would just be mg is equal to g, and we'll call this m1, and this is m1, m2, all over r squared. So it is also possible to equate the two of those together, because the force of gravity is what causes your weight. Those are equal. F sub c is equal to F sub g in orbiting bodies. Remember those two things as you work on the homework, and I will post the homework assignment on the side where the assignments normally go. All right, let me know if you run into any trouble with these. Those two big facts are so important. F sub c is equal to F sub g in an orbiting body. Also, your weight is equal to F sub g in that long expanded form. Keep those both in mind, and these should not be all that difficult.